Hey everyone, and welcome. Today we're going to jump into something really cool, one of the most powerful ideas in all of calculus, actually. We're talking about how to take messy, real-world situations and turn them into these beautiful, clean mathematical models that we can actually solve. So think about it for a second. What could a tank of salt water, a booming population, and a falling object possibly have in common? I mean, they seem totally different, right? You've got chemistry, biology, physics, but what if I told you there's a single mathematical idea that connects all of them? Yep, you heard that right. The secret sauce here is this one incredibly elegant idea, a universal law of change. And trust me, once you get this, you are going to start seeing it absolutely everywhere you look. All right, so let's dig in. We're going to start with this core principle. Think of it as the engine for all the modeling we're about to do. It's called the universal conservation law. Now, it sounds kind of fancy, but honestly, it's super intuitive. Just picture a bathtub. The rate at which the water level is changing is just, well, it's the amount of water coming in from the faucet minus the amount of water going out the drain. That's it. This rate in minus rate out concept is the absolute key to everything. And here's how we actually build the math for it. We start with something, some quantity, we'll call it Q, that's changing over time. So its rate of change is, of course, dq by dt. And where does that change come from? It's just a tug of war between what's coming in and what's going out. That gives us our golden equation. dq by dt equals rate in minus rate out. This simple formula is our master key. Okay, so to really see this in action, let's get our hands dirty with a classic textbook problem, the tank mixing problem. It's like the perfect little laboratory to see how all these pieces work together. So here's the setup. You've got a tank, and inside there's some amount of salt that's changing. That's our Q of T. We've got salty water, or brine, flowing in, and at the same time, this perfectly mixed solution is flowing out. Our whole goal here is to figure out a way to model Q of T, the amount of salt at any given moment. First up, let's tackle the rate in. How fast is salt actually entering this tank? Well, it's pretty straightforward. You just multiply the flow rate of the incoming brine by how salty it is, its concentration. And you can even check your work with the units, right? Gallons per minute times pounds per gallon. The gallons cancel, and you're left with pounds per minute. Perfect. That's our rate in. Okay, now for the rate out. And listen up, because this is where people almost always get tripped up. The liquid is leaving at a certain rate, R out, sure, but what's its concentration? See, since we assume the tank is perfectly mixed, the concentration of the stuff flowing out is the same as the concentration inside the tank. And what's that? It's the total amount of salt right now, Q of T, divided by the total volume right now, V of T. And here's the kicker. That concentration is constantly changing. It is not a constant number. That's the big mistake to avoid. And yeah, speaking of volume, that might be changing too. The total volume at any time t is just whatever you started with, plus the net change. And the net change is just the inflow rate minus the outflow rate times time. Now, if those two rates happen to be the same, then your volume stays constant, which, makes our lives a whole lot easier. And there we have it. We just put all the pieces together. The rate of change of salt, Q prime, is our rate in minus our rate out. Just like that, we've taken a physical setup and translated it into the language of calculus, a first-order differential equation. Pretty cool, right? Okay, so setting up the model is half the battle. But now we got to actually solve the thing. So let's grab a real concrete example and walk through it step by step to see how we get from this equation to an actual number. All right, here's our mission. We've got a tank with 500 gallons of pure water, so no salt to start. We've got brine flowing in at 5 gallons a minute, and the mixed solution is flowing out at the exact same rate. Now, since the in and out rates are equal, our volume is going to stay a nice constant 500 gallons. The big question is, exactly how much salt is in that tank after 10 minutes? Okay, so let's walk through the solution. First, we plug all our numbers into that model we just built. The rate in is 5 times 2, so 10. The rate out is 5 times Q over 500, which simplifies to Q over 100. So we get our DE. Q prime equals 10 minus Q over 100. From here, it's kind of the standard playbook for solving this type of Renier equation. We rearrange it into that standard form, then we bring in this special tool called an integrating factor. It's what makes the equation solvable. After we work through the integration, we get what's called a general solution. It has that plus C on the end, which means it describes every possible version of the system. But we only care about our tank, and this is where the initial condition is so important. We know our tank started with pure water, right? So at time 0, the amount of salt, Q, was 0. We plug that in, and it lets us solve for our specific C. And once we have C, we have our final, unique equation that perfectly describes the salt in our tank at any time t. And now for the big reveal, we take our beautiful new equation, we plug in t equals 10 minutes, run the numbers, and bam! We get our answer. After 10 minutes, there are about 95.16 pounds of salt in that tank. I mean, think about that. We went from a word problem to a precise physical answer. That is the power of this kind of modeling. But here's what's truly mind-blowing. This whole framework isn't just for mixing problems. What makes it so incredibly powerful is that you can apply the exact same logic, the same rate in, rate out thinking, to fields that seem totally unrelated. Let's take a look. Take population growth, for example. You've probably seen the model P prime equals KP, where the rate of growth is proportional to the population. But have you ever stopped to think about what that constant K actually is? It's just the net change. It's the birth rate, that's your rate in, minus the death rate, your rate out. It's the exact same idea, just with different labels. And this is my favorite one. It's just so cool. Even a falling object follows this rule. Look at Newton's second law here, set up for velocity. The rate of change of velocity, v prime, has a rate in, that's gravity, constantly pulling it, adding speed. And it has a rate out, that's air resistance, or drag, which is working against it, trying to slow it down. Rate in minus rate out. It's incredible. So, what happens when the rate in from gravity exactly balances the rate out from air resistance? Well, the net rate of change becomes 0. Your velocity stops increasing. And what do we call that? That's terminal velocity. It is the system's equilibrium point, where rate in equals rate out. It's the exact same concept as the salt concentration in our tank eventually leveling off if we just let it run forever. Wow, okay, so we have covered a ton of ground, right? We went from the basic idea to building a model, solving it, and then seeing how it applies to all these other areas. So let's boil this all down into a simple, step-by-step framework that you can use for pretty much anything. Here you go, your very own modeling toolkit. 4 simple steps. 1. Figure out what's changing. What is the actual quantity you care about? Salt? People? Velocity? 2. Define the rates. What's adding to it? What's taking away from it? Get your rate in and your rate out. 3. Build the equation. This is the easy part now. dq/dt equals rate in minus rate out. And 4. Solve it. Use your starting point, your initial condition, to nail down that constant and find the one specific solution that matches your problem. That's it. That's the whole game. So, I'll just leave you with this one last thought. We've seen how this one incredibly simple idea can model chemistry, biology, and even physics. So now, I want you to think about your own life. What about the money in your bank account? The number of unread emails in your inbox? Or, heck, even your own happiness or stress level? What complex system in your world could you understand a little bit better just by thinking about it in terms of rate in and rate out? Something to chew on. Thanks so much for joining me.